Okay, so good evening, everyone, and welcome back to the series of All About Neutrinos, an online interactive lecture series for general audience. These are being organized, as you know, many of you know, by the INO project, the India-based Neutrino Observatory project. And many of you, in fact, have in the past requested seeing various lectures and on varied topics, both covering the neutrino physics in general, high energy physics, new, you know, nuclear as well as astrophysics. So there were some requests from some of you asking for specific topics that you would like to have them given by the experts in the field. And one of the most popular ones that everybody requested is a talk on simulations in high energy physics. That's not really surprising because simulations has been the main focus and main area of many of these experiments, especially the bigger ones that are coming up. To study the physics, the feasibility, and many other things. And of course, no other person as qualified as Professor Majumder, Gobinda Majumder, on this particular topic. And since many of you know him well, I'm not going to make a very formal presentation on about his CV, but except to say that I'm sure many of you once again know that he had developed complete INO simulation and reconstruction code from scratch. And also, of course, after that, he has trained generations of students who actually took over from him and added some code. And that is how this is going on for last many years, close to probably 10 years or even more. So today, he is going to give, as it was announced, the first part of this lecture. And knowing that the field is a bit vast, so obviously there will be also a second part coming right after the that is next Monday on 9th November. Okay, so these are the two series, but we'll hear more from him, and based on how things go, you may have some other plans how to continue and so on. So without taking actually more of his time, I now request President Govinda Majumdar to start his lecture.
Okay, thanks, Shotto. You can hear me?
Yes.
Okay, and about screen?
Yes, perfect.
Okay, so, okay, thanks, Shotto. And Shotto has requested me actually long time. I was delaying. But then he told me to give one lecture on the simulation and reconstructions. But to me, it is very difficult to convert in one lecture. So I thought maybe I'll give the two lectures, one on mainly on the simulation and the second one on the reconstruction plus calibration, etc. But even though today the way I prepared looks like it will go beyond 1 hour, if you are too much exhausted or bored, just let me know. Accordingly, I will stop or I will skip some materials. Okay, so now when you talk about the simulation in high energy physics, okay, and first of all, as Shotto says that I developed the code, that's true, but I am not an expert of this code. Let's, for example, Giant code we are using. I am using what is the Giant tools provided us, just user of that, and using that we design our detectors. And also same way I say that when the official package is there, for our requirement, we may have to tune some of these parameters and just change this code just which is suitable to us. So I am in that level, not the exactly the Giant4 code developer or like that. Okay. So then I will just again give some of my experience, or let's say in the last many years, whenever the defined code we developed and what was there. And also I took the many information from many different people talks. I just put it here the list. And also some of the official web page of this CMS Atlas collaboration, also Genie, PTR. This is this generator groups, their web page. Of course, Giant is one of them. Okay. So now let's say this is our detector right hand side. So we are seeing the signals, but before making our detectors, we want to predict what would be the expected results in our experiment. That's the main context for our case, that we will use the simulations. Okay, so now I'll just in short introduction, I'll give the very brief introduction of these simulations, from where it started, and some basic logic of the simulations. And actually I may be bored some of the senior people. I will give this very fundamental logic of this simulation, that is the so-called random number generators. I will start from there, that I'll spend little bit of time. Then we'll talk about the simulation in collider experiment. And in the simulation stage, we say there is in general 3 steps. One is this generator level, means this is this when the collision occurs or the particles are produced. But then when the particle goes to the detectors, we see the some interactions. That's we call the simulation. But what we see in the real experiment, we do not see the interaction. We see there's some electronic signals. And that means the whatever the interaction happened, that affected, produced something, and that we collected as electronic signal. That's we call that digitization. So all of them, I will try to go through this, and then also we'll try to see the simulation of atmospheric neutrino. Let's say for iono case how we do, and then conclusions. Okay, so simulations are simply the word. A computer simulation, usually at present we always say the computers, but when earlier it started, it started not with the computers. Applied the mathematical method to the analyzing of the complex real world problem and predicts what might happen depending on the various action or scenario. I will elaborate more details and use simulation mainly. This is the 3 points I mentioned. Doing this actual experiment is not possible. For example, cosmology will look for this universe, but only one universe. We cannot do this experiment. We cannot make it. So that's why there's a defined model. We do the simulation in cosmology. Some cases when the cost in money or time or danger on the experiment is prohibitive. So let's for example nuclear reactors. So that time also try to use these nuclear reactors. And then the system does not exist. For example, as I said, this our ICAL detector, at present it is not there, but we try to, using the simulation, we try to design it to extract the best out of it. So these are the main 3 things. Then now if I go to the next, if I go to the brief history of the simulations, this method, the simulation method formally developed by Newman during World War II, but already it was known earlier that this Fermi uses the simulation for the neutron diffusion in 1930s. He knew the behavior of a neutrons, but he did not have the formula how to the system of neutron would behave. And that time he just used a table of numbers sorted on the roulette to obtain the random number, which he then used to calculation of the neutrino absorptions. So that was this very early time. But then actually in the same concept he was used. He also used it to demonstrate the stability of this first man-made nuclear reactor at Chicago in 1942. This is some old pictures. His model had an analogy of the heat diffusion models which was earlier developed. And actually now if someone asks me that how people allow him the simulation which was never used earlier, and the this is the nuclear man-made nuclear reactor, that time there's most likely there will be a blast. But people are trusted so much on him that on this model he was allowed to have this experiment in the crowded area in Chicago. And that's actually, to me, it is one is emerging people how much trust he has. Before that, there is no simulation, nothing was there. And on just trust, it moved. Okay, then now come to the, if I go to the next. So, as I say that, von Neumann developed this present day simulations, but if we have to say that Manhattan project, in that time, there is a 3 person was there, Newman, Ulam, and Metropolis. And that time, those people are trying to use the construct the damper and shield for the nuclear bomb. And experimentation was too time consuming and dangerous. So that was the time. And some, okay. And this Ulam was interested in plotting the outcome of his games at casino. Actually, he was this Manhattan project, but he had a brain surgery. So what to do that time? He was idle in the home. And that time he was just trying to see what was coming in this casino, the outcome. Just try to see those and try to see this, how this observe that distribution and determine the probability of winning. And he has a knack of this because he originally, I think, from Poland. One of his uncle, this is Michael Ulam, and many times this was Ulma. This is this Stanislaw Ulam. He used to tell that my uncle go to the Monte Carlo for the gamble. So that's the name of the Monte Carlo. So this okay, again I'm saying Ulam. He was trying to just see this, how this number, different days, different times, different number comes, try to correlate it, and just try to get this, how can get this, what is the probability of winning or how you can win. So this was with this gamble, that number he used. And then he said that this I have done with this casino's number. And then he talked with this Newman. And then Newman was first developed this real simulation package, and that the simulation package to develop, and it was used in these Manhattan projects, and then gradually extensively used many disciplines, especially after the advent of high-speed computing. I will come why this high-speed computing come into the pictures. And then also many other things. I will not talk about anything on this cancer therapy, traffic flow, forecasting, oil exploration. Many places people use these simulations, and I will talk about only in terms of the particle physics. And so this is something I am not in this. Something went wrong in these slides. Okay, so this is this, we call this in Monte Carlo. This is the place in Italy, and this was the famous for the gambling. As I say that Ulam's uncle used to go regularly, and if you see these general lectures on your simulation, you will mainly see these two photographs. I think one of this place of this Monte Carlo, and another is this. This is the one of the casino. Okay, so this name came from this place. And so in general, we say the Monte Carlo, a numerical simulation method which was used a sequence of random numbers to solve a complex problem. Okay, and actually in high energy physics, we use this word Monte Carlo simulation. Sometimes use the simple simulations, but we usually use the word that Monte Carlo. We do not call the simulation. Usually very common, we will see this in energy physicists will talk that data versus Monte Carlo. They do not say that data versus simulations. So it is Monte Carlo simulated event, but this Monte Carlo name came from that casino or this Italian place of this Monte Carlo. So in my talk also, many places I will talk Monte Carlo simulation, sometimes simple Monte Carlo. Okay, now with this Monte Carlo, when you go, so as I say that Monte Carlo means a numerical simulation method which uses the sequence of random numbers. So now I'll spend little bit of time on the random numbers. So when you say the sequence of random number is a set of number that have nothing to do with this other number of the sequence. That's the things. And in a uniform distribution random number 0 to 1, every number has the same chance of showing up. For example, 0.001 is just as likely as 0.0, some arbitrary numbers. So to obtain the random number, which, as I say, that you go to the casino. This is this what people use, roulette, lotto. This is the some numbers, but often this is from this casino, some number you go. Actually, this was the it was okay, not in the official paper, but if you go, people talk that this Elam's uncle used to go there, and he used to tell that this is the sequence of number I see in this casino today, and that's the number Elam used to use in his initial early design of the simulations. So that's this of this true random number from the casino. And of course, in our physics, we can say that we can take the sequence of the radioactive decay or arrival of cosmic muon time. That's also random number. And actually, tables of few millions truly random number are exist until few years back, but now it is more. But at present, so that means we have these true random numbers. But even though we say that few million, that is not enough for the most of the applications. And also, hooking up with the random number in a machine to a computer is not too good, as it leads to the irreproducible result, making debugging it difficult when you write our programs or predict something. We want all the same sequence. So that's the why we call this, we developed a pseudo random number generators. And I will talk about little more on this. So as I say, that random number, they can take the any value from continuous 0 to 1. So this has a functional, let's say if it is a functional forms, I can write down this fx dx. This is the probability of this having this my number x between x to x plus dx, and it has a probability is a cumulative distribution functions. And only thing is that this property we use, integration of fx dx that equal to 1. Let's say this is my one of these functions, and this is the range. Below this range it is 0, above this range it is 0. So if I integrated the whole thing, it goes to 0 to 1. That's the total integration numbers. Okay, so that's this principle we used when you go to the random number generators. Okay, so first we go for the uniform random number. Actually, Newman's what first developed the random number. This was his model was what it called the middle square numbers. Just take an arbitrary any number. I just put it 89569856. Just take, this is the first random number. Take the square of it, and this is the square of that, and then take middle 8 digit of that square. Okay, so that will be the second random number. Then now make this 7591 that number 3891036 square of it. Again take the middle number. That will be this your a third random number. That is the way you can go to this arbitrarily large sequence of random numbers. But this does not gives you a large sequence of number, and also depending on this initial seed, sometimes this number converges very fast. Okay, so this will, though initially it was developed, but this is not used at present anymore. But this long time, this is the standard random number was used. This technique was called the multiplicative linear congruent generator, MLCG. So here it says that I have a generator random number, some ith random Ri, A, C, M. These are the three just integer number. You take this A into Ri plus C, that mod of this M, that gives you this new random numbers. And this is the random number. This is now you have a new random number. So again, you use this formula, go to the next random numbers. But these random numbers having a correlations depending on the seed between the two numbers. And actually, this is once I have to tell Acharya might remember these things when Shumanta used to simulate our C217 stack, and the simulation we saw that theta and phi there is a correlation, and we spent a lot of time to understand what is the problem, and this problem was in the generation of random number. And right hand side here I just show a plots. Here x-axis, y-axis, z-axis. X-axis is the first random number, y-axis is the second random number, z-axis is the third random numbers. If you just these three sequentially number you put, you see these first, second, third random number, they are not completely uncorrelated. There is some correlation is there. Okay, so this was the drawback, and actually this was George Marsaglia first mathematically formulated this, and he showed that even it is the some number in the 3-dimensional it does not show any correlation, but in the 4th dimension it might give a correlations. So basically this has a problem of this correlation of these different random numbers, and then he came up with this simple formula with these two independent numbers. This is just a mathematical formula, otherwise I just write a constant number into a random number, random seed, two random seed, a random seed with this bitwise OR of 2 to the power 16 minus 1, and plus another random seed, you shift the 16 bit and add these two, get this new this seed number. Similarly, come for the second seed also you modify, and then return the number. This is this, okay, this is this mz, shift in the left side bit and added with this mw, that gives the new random numbers. Okay, that's the return. This is the number. Second time when you go, by that time mz and mw are changed here, and they will give you the defined number. And this was his concept, and this was the little bit of modified by Martin Lusser, and that's the was used in this. Okay, I just put T random. Actually, this is the for the students. Most of the high energy physics students use the root software, and this T random is used this MLGC's T random, okay, root random number generator that uses the MLGC algorithm. T random one uses this Lucier, where you modify this Marcel's code. That was the T random one. And then this number also, it is not sufficient. It goes up to 2 to the power 60, 2 to the power I think 64 minus 1 number. Then this was generalized. Instead of 2 number, it go to the 3 or 4 number. This is the 2 seeds. Instead of 2, we go to 3 or 4 seed, and that was developed by Pierre Lequer, and that number go up to 3 or 4 variables, so it can go 2 to the power 88 or 2 to the power 113 numbers. That's the periodicity of this random number, and that was used in this T random 2 of root software. Then this is come by this Matsumoto and Nishimura. They have a long jump, and they go, instead of 4 dimension, it go to a 263 dimensional equidistribution uniform random number, which is the period is 2 to the power. This is the 19937. This is that's the 2 to the power this minus 1. That many bits. That's a 32 bits. So this number is 32 into 263. That many numbers. Sorry. This is the 2 to the power 263. That many numbers of this we can use in the sequence, and that was used in the T random 3 at present. So this is just an uniform random number, but in real world, when we do the simulation, we do not go for the, most of the times, not the uniform random numbers. We have to go for the other random number depending on this function. If it is this, let's say radioactive decay, then this will then this will be this your exponential functions, or this Gaussian distribution, Poisson distributions. We have to generate the numbers. So we start from the uniform random numbers. So let's, for example, exponential distributions. So this is this, we say that this is the y is equal to e to the power a minus x. Always keep in mind when I'm talking about the random function, this is the normalized function you have to talk. So y, it depends on the x. So now let's say I have a function fx. This fx is a function, fx dx, it is 0 to infinite integration is 0 to 1, and y, it depends on x. So now this is the pictorial form I just show. Let's say this is my x-axis, and this is the fx. It goes like this way, and y is related with this x. So this, let's say y is this, and the gy, another function. This I plot like this way. Now keep in mind, y is in one variable, x is another variable. but gy dy, this total integration equal to 1. Similarly, fx dx, that integration also is equal to 1. And also, if I go for this x, well, let's say this is the value of the x and there this is the value of the y. When it x move to x plus dx, this is the fx dx, this is the probability of becoming x to x plus dx. X and y are correlated, so y go become y to y plus dy, the probability of this fy dy. But this, we know that this both the probability should be same. So just that the technique we use, this is the when the two correlated variables, the probability distribution functions, this probability are same. Now you assume this one of the function, this is the uniform random, fx is the uniform random number from 0 to 1. So use 0 to 1 fx. So fx is equal to 1. So that means dx is equal to your gy dy. Now if you do the integration of that and that inverting this function, you will get y as a function of x. So x will generate as a uniform 0 to 1. But using these functional forms, we can now get this y, which is my exponential or other functions. So this is this very basic concept to use. But again here, I will come to show some example. This is the functions. I say that inverting this function y is equal to y as a function of x. So this is the y, this function has to be continuous. It has to be analytically integratable. But most of the functions what we use, we do not have that integratable analytically integratable functions. So sometimes we use this PDF is continuous but not conventionally integratable functions. Actually, this technique is not much used. But another technique was used when this probability distribution function is not continuous or not conventionally integratable. And this is a waste of time, I say. Let's say this is this function, this is the arbitrary functions we have, and we generate the random number based on generate the random numbers according to the arbitrary function using what we call the acceptance and rejection method. And actually in between, Gaussian distribution functions, even though this is the very commonly functions, but using the simple integration, we cannot invert the Gaussian functions. So in 1958, Box and Muller, they developed a new techniques using the two random numbers. They can generate the two uniform random numbers. They can generate the two Gaussian numbers distributions. Also, people use the central limit theorem to calculate these Gaussian functions. So these are the different techniques. When we have the functional forms, you generate your distribution, predicted distribution, random number for the predicted distribution using this one of these techniques. But here in the last few words, I say that waste of CPU time. So if you have these exponential functions and just try to use these acceptance rejection functions, then you lots of number you will lose. So you unnecessarily spend lots of CPU time. And most of the experiment, most of the our case is not in general. We have these integratable functions, but what we used to do is I say that in real experiment, all these expressions are too complicated for the function you will come. I will show one or two examples. They are not conventionally integratable, and acceptance and rejection method takes the too long time. So there is that we say that we use the combination of the acceptance rejection method and variable transformation method. For example, I say that I have a functions which is the exponential into a gx function. Gx is nearly flat distribution. I say gx is log of 1 plus 0.001x. Okay, so this will very close to 0, and then it will move to gradually go up. So in this cases, what I will do, the way that it was done, first generate the random number using the exponential functions, and then using the acceptance and rejection method, you choose that x you will select or not. So this is the combination of acceptance and rejection method and the uniform random numbers. But in real life, even it is much more complicated. And generally we use what we call the composite model. Composite model means here I say that fx is a function of this exponential plus gx. Like that, many of these functions. We call the alpha fi gi. This is the fi is this one of the exponential function, and gi is this another function log of 1 plus x. That's I'm saying. And this number, this is this expression we write down this form such a way that the gi is varies from 0 to 1. All the alpha is greater than 0 and fi is greater than 0. With this condition, this fx dx is equal to 1. Now, using this random numbers, again, first we choose which, depending on this value of alpha, I choose that which function I should use. Then according to the functions, when I choose the functions, then I go this form. According to the function, I generate the x. Then I go for the accept and rejection method to choose that function, that value of the x we should use or not. And this is a simple example. I say the Compton scattering. If you see this Compton contains cross section, epsilon prime is this energy loss. That's the this h nu prime by h nu of the Compton scattering, and this is the expression we write down. And here we say that both are the same g. G is these functions, but this is this my f is this 1 by epsilon by and just epsilon. And here alpha 1 and alpha 2 are the different due to the normalization of this fn1x and this f2, these epsilons. Okay. So now this is this one example I just tell you. Usually in the student I used to tell that this is this very first example where you will see a complicated random number generator, but this expression you are familiar with this and you can start with this expression. That will be this you're giving a good confidence about to random number generator for any functions. Okay, then now okay, after that basics I just again recapitulate. When we say the general concept of Monte Carlo method, Monte Carlo simulations or Monte Carlo integration usually called, I will only talk about the simulations, but generally as I said that again it developed in atom bomb in 1940s. It is a mathematical approach using a sequence of random number to solve a problem. This is the punchline. Refers to any procedure that makes use of random numbers, usually when it's a Monte Carlo method. Any method which uses a random number, uses the probability statistic to solve the problem, or a class of computational algorithm, can be applied to the vast range of problem, are not, but this is not a statistical tool, rely on repeated random sequence, provided generally approximate solution. So this, it is not that analytical. So we have some approximation. It will not gives you the exact solutions, and are used in the cases where analytical numerical solution does not exist or too difficult to implement, and can be used for the lazy scientist when the analytical numerical solution can be, means it has tried to avoid it and just use these random numbers. And as I said that this Monte Carlo method, it uses the numerical integrations, error estimation, optimization, and numerical simulation. Again, from the standard textbook, I just give an example when we call the Monte Carlo integrations. I think this is almost all the numerical recipe. This example was started. I have a, this is in shape of an torus. This is something, this condition is that this is the z square plus x square plus y square minus 3 whole square less than equal to 1. So I have only this much. X greater than 1. So this is the x-axis. This is the positive side. Y greater than minus 3. Y is this. It will go like this way. And this condition will say that this will be restricted on this. And the density of the torus is goes e to the power 5z. Now in this torus, you calculate what is the mass and what is the center of mass and the center of mass position x, y, z. And how do you integrate it? And we may calculate in this different shape we can integrate, but simply if you can random number generators in the random numbers, I can calculate it this approximately what are these all these mass and center of mass. Okay, then now come to this our case, another examples. Oh, sorry. Why it is coming like this way? Okay. So this how we use these random numbers? We say that we have some theory with some assumptions and do the experiment, and that gives the verifications of the theory. And now theory takes some assumptions, and this experiment gives you these assumptions on this theory Monte Carlo, and we do this small correction on this experiment. And this is this way theory gives you this some assumptions, and the Monte Carlo is simulated, and experimental we see something that gives the feedback to the theory, and on that, based on the theory, we simulated, and the experimentally data, when we see, we verify that the Monte Carlo simulation are right or not. If it is required, we tune some of this little bit of corrections in this Monte Carlo. Okay. So now let's see, this is an one first and basic example. Again, this is I think from the textbook. Calculate the value of pi. So how we can do this? Generate a random number in two-dimensional, -1 to +1, and just x and y, this is -1 to +1, and just accept the events where square root of x square plus y square less than equal to 1. And now you calculate it is n accepted by n total. That number, you know, the total area is this 4. This is the length is 2 into 2, 4. But the circle of the radius r, circle is this pi r square. So that means, so the pi into r square is equal to 1. So that means that how many events in the randomly, if it goes within this circle by this total number, that is the pi by 4. So this is the simple. Now the point, this pi by 4, if we generated the one event, it may go outside or inside. Then one event, how you can say this is a pi value 0 or 1. But when you go to the two event, it may go little fluctuate 3 and 4. So with these numbers, we can get a value, but also you can calculate the error. This is the binomial distribution error you can calculate. Now when this number of tries, how many events we simulate, even though the number is increased more and more, and this is the one of the sequence, I get this value of this, and this is the error. And then now when you go for this more and more numbers, then your error is gradually going smaller and smaller, and you see your number is coming closer and closer to the 2 value. So the computer power is an issue, and how long would it take to throw this many darts? That's why the Monte Carlo method has become popular only quite recently, when we have this computer and also we have a powerful computers. Okay, earlier we did not have that, because our prediction we did it, but there is not much precision we had because of this limited number of events. Okay, so now come to this. Okay, I spent more than half an hour. Now I come to the real high energy physics simulation. And let's see, I will simulate this LHC experiment.
Gobinda,
Yes.
just about an inquiry. So if there are some questions,
Yes, anytime.
You want to, because this is now just one part you finished. Let's take some few simple questions that were there on YouTube. So for example, what will be course of action if any discrepancy is found between the simulation and the data available? I mean, of course, this you will probably deal later, but there was a question. If you want to answer.
Okay. So that's why I'm saying that this is the many thing is the assumption, verification, assumptions and verifications. So when the data in Monte Carlo does not match, then we have to say that what assumption went wrong when we design our experiment would give this result. So we have to look on that which assumption was which was not correct. In general, okay, I took my simulation boss, that Sunanda, he used to say that data is data. We can't do anything with that. Only we can tune this simulated event, and that's we tune the parameters or our knowledge such that this is our simulation was matched with this real data.
And another question again from Aditya Mishra is how can we infer if a given data set is truly random? It could be that it is random for the given data set, but a part of a larger series or sequence.
Yeah, so that's why in any experimental data, it has an error associated with this. That tells you this how reliable the data is. So if the Monte Carlo, let's say that here is this number, my experimental number of pi value, if it is coming 3.1 plus minus 0.3,
Okay.
so then I can say that this is this value within this true value of pi within this error, but my measurement is not good here. But when it comes to the 3.14159 plus minus 0.0003, then I can say that my experiment is and this is very precise experiment. It gives the true value of the pi. Okay. So now we have to trust this experiment. Actually, that was my main talk was last few weeks back. That if this experiment says that my number is 3.1, but error is 0.00003, then we are in soup. We are trusting this experiment, but the experiment, this is the who published the result, they are lying. So in that case, we cannot do anything. We assume that when the experimental result published, they quoted error. In the error, they estimated all the concern such that when you do the repeated experiment, or if whose true value is lying within this mean value and within plus minus 2 or 3 sigma of the error. That's the confidence level. Within that confidence level, you can say that if I do this experiment again and again, 67% of the time my value will come 2.8 to 3.4. Okay? So we have to rely on this experiment, the result. We trust on it, trust on them. What are the error they quoted.
Yeah. So, and I think you can go ahead now.
Okay. Okay, so this is is collision Large Hadron Colliders. Okay, I think most of the people know this, but I'm just repeating. This is the 27-kilometer tunnel, proton and proton going in the opposite directions. Beam of the proton is about 6.5 TeV, and roughly the arrow has in 2556 bunches, and each bunch is turned 11,000 times. This is the hertz rate the bunch is moving, and this is the each bunch roughly this is the 10 to the power 11 protons are there. Okay, and then this is the luminosity number I ignore, and the gap between the two bunches is 24.96 nanosecond. And when the two bunches are going opposite directions, and here is this picture, there is a lots of protons in the both bunches. When you come close together, they will collide. But we know that proton is not a fundamental particle, so proton will not collide. Within the proton, the quark or this gluon or the parton, I have a next, I have a one slide on this. They will collide. They will produce the sum of these particles. It may be Higgs or this SUSY. Just here I put two things. Higgs decay to the 2Z and that good the 4 muon, or this supersymmetric particles, and we pretty expected that how many event we will see. This is this we say that this is the our old experimental knowledge. From that the luminosity, if I know, we know the cross section from the theoretical models, this branching fraction, our detector efficiency, etc., etc. If we calculate, we can calculate the total number of event. So that's the thing we expect. And then in the real experiment, let for example, we'll see this is the Higgs to ZZ event. This event, there's a 4 muon goes in the 4 different part of the detector. This is the real event. But before the CMS was built, we have to make these simulations and try to design our detector such that a real experiment we can clearly see this kind of an event. And then eventually, this is the Higgs discovery in 2012, both Atlas and CMS, they have shown this is this 4 lepton channels, this is this 4 leptons uh, peaks coming from the Higgs, or the Higgs decay to the 2 photons, this is coming here, this is the peak. So that was the established. Now, this talk will not this result, this talk will the main thing, that before we have the CMS experiment or the Atlas experiment, how do we predict that we will see this kind of an event if the Higgs is 125. If Higgs mass is, before the LHC experiment, we did not know what is the exact Higgs mass, but that time the speculation, if the Higgs mass is 125, how do we best see this peak? Or Higgs mass is 200 GeV, then what is the best way we can design our instrument to get to see that peak? So that was this simulation was totally depends on that simulation to design these detectors. Okay, so now in this simulation when we talk, it has a many different steps. As I earlier says that in the simulations, when first this proton-proton collide, that is some interactions happen. This is the pictures I show, some proton-proton interaction, many particles are produced. So this is given by the standard called the simulator package. Then this, when the particle come, this particle will not see directly. Particle will, let's say Higgs, I say the Higgs decay to the 2Z boson that goes to the 4 muon. We'll see this muon. How do you see the muon? Muon go to the detectors. How that there they keep a some signal on it, detector matter, it interact with the detector material, that gives them signals. So how they interact with the detector material and how they affect our signal strength, that is determined by these simulations. And for that, in general, there is a many simulations, but most of the high energy physics experiment we use the giant simulations. That is for almost every experiment to use it. Maybe just the giant or slightly tuned of the giant versions we use it. Then this is this, as I said, this detectors interaction, but when we see some electronic signals. So in the electronic signals we say that we simply word use called the digitizations. So this particle interact with the medium, this produce some signal, somehow we collect it, and it is either scintillators or the electrical charge. And when you collect it, that is the digitization we do. And that was this, actually this is very specific to individual instrument or individual particle, how it goes. And this has to be specific for each and experiment. Depending on the scenario, it will vary. And then when I see the signal, this digitization part, simulation up to this level, what I am coming here, in the real experiment also, I will have this, supposed to have the same kind of digitized signals. Okay. So now in the simulation, in this step, either any one of the step is something is going wrong, or I would not say that something is going wrong. Some assumption was not true, what in the real experiment, then my simulated output and the experimental data might be different. And then one of the signals we will see in the different instruments, and then we'll go back from that signal, we go back to reconstruct these individual particles, that we call the reconstructions. And today I will not talk on that, I will talk on the next day. Okay, now in the simulation there is a many steps. First of all, as I say that this is the proton. Basically baryon and meson, they are not the fundamental particle, they're made of these different combination of the quarks. Here is an example, I say the proton or the neutron, that's So this is many of these quark and gluon. So when this interaction occurs, interaction of the proton, so this is the protons. So just a second. How do I make this
What you want to do?
pointer?
Right click and that one. That one.
Okay.
That is
So
laser.
yeah. Why it went to that back? Ah. Okay. So this is this interaction occurs. There is a proton. So when I'm saying this proton, there is a many particles are here. Similarly, the second proton also many particles. And one of the here is this parton we call it is either quark or the gluon. This both of them they will interact and produce something, and that we will see. Okay, so we see that. So this interaction is not a protons. We see the interaction of these partons. Okay, now first thing in the simulations, that when the proton is collision is occurs, two protons are coming for, and let for example in Tevatron proton antiproton, what is this probability distributions that I have a quark, let's say I have a new quark of momentum x, momentum x size, the momentum is this momentum of this proton by momentum of the proton, fraction of the momentum carried by this quark, and it has a certain distributions. So well, very first steps we are supposed to take care of this is the what is the, depending on this we have to see that what of the quark, what is the probability of this quark has a fraction of momentum of let's say 10 to the power minus 2 or like this. This is for the different quark flavor and the gluon it's shown. Okay. So this is the we are supposed to take in this from the distributions we are supposed to take, but in general in reality we take it slightly different way. And then the point here we say again the same thing I repeating. Usually we say that this is the two parton was interact, it produce these two leptons or two parton go to the gluon, produce the TT bar and then give the W, and then this is this signal we will see. Okay. So this is this generating process. So basically we first choose a quark, and then quark, what is the momentum? Depending on this momentum, we have the two quark or anti-quark or this. Okay, I just say the two partons, they can annihilate and produce the sum of this process. If I want to go for this gamma star to two leptons, then this is the steps we have to choose that which process we should use. And if you go for this process, in this generated level, you have this many different processes. Okay. So again, using these random numbers, you have to choose that which process you want to simulate out of this many of these random, depending on this different process has a different cross section. So that means the probability of interactions or probability of having different processes are different. Depending on that, you will have the different kind of an interaction, different kind of an productions. But that is also not reality. Actually, if you go to proton, this is much more complicated. So I just talk about this part. This is this one parton, and this is the another parton is coming and produce some process is happening here. But in the real scenario is something like this. So this is in one quark, one parton, and here one parton. Before it collide, before it makes is this my Q stars or this gamma stars, it may emit say emits a Bremsstrahlung, or it may emit the what we call the initial state radiations. So there is some more things can happen, and then this is the particle when it produce this interaction, something is produced. But as we know that quark and parton, they are not the free particles. When it goes, they fragmented of the different particles, and eventually they here when this in this case here they form a big circle. That's I call that this will call this is the hadrons they produce, and then they go to the hadron, they will be the decaying to this hadron. So first this is the quark and gluon, many quark and gluon will produce. They combine to form our colorless neutral hadrons. The neutral hadrons, they will decay. So this is this one way. The other side, this is the two partons. So the remaining proton and two protons, this also carried a colored. So this also become a colored. So this particle, this, and also we know that eventually we do not see the colored particle. So all of them had some interaction such that eventually we will see the colorless parton, that we call this interaction of the beam remnant. Sometimes it happen, this is the two parton interact, but this another two partons of this quark also interacts. That's we call the multi-particle interactions or underlying event. So this whole process is happening. Okay. I cannot explain you this all the detail, how this all of these stages, how we choose these random numbers to go from this my initial proton to come to this, all this pattern. So all are there, every stage means here I say that when this is one of this gluon, it's split into the two gluon. What is this probability? This is the ultra-Parisi, the shower development, we know. This is the one gluon to two gluon. This is a jet, means initial gluon has a momentum. If the two gluon, one momentum carries the fraction of momentum z, another will be 1 minus z. What is the probability of that? Similarly, a quark go to quark and gluon, then what is this probability? And this, all this probability we will calculate, and based on these numbers, this functional form, we will have the distribution that when this gluon goes, it will, how it will go. Okay, so that is the way we call this is the parton showers. And then I also mentioned this is the second parton may produce, that we call the multi-parton interactions. Then this is the initial state radiations or the final state radiations. And actually initial state radiation and PDF, they are correlated. When the initial state radiations occurs, the I say that I choose the two partons, that the same energy of this parton I choose. So accordingly, you're supposed to give the interaction. But there's the initial state radiation occurs, my center of mass energy is changing. So I cannot just isolate the parton distribution functions and this ISR. They are combinedly, we have to take care of it. And also in the eventually when this is will go finally, the beam named and usually call the color deconnections, means all of them again combine together to form a neutral hadrons. So that's also factors as to take care of. Okay, so this is this very complicated things. Okay.
Sir, can I ask one question?
Yeah, yeah. Okay.
Yeah, so I think it's slide number 20. So you have shown that there are, yes. So there are different processes. So if we are, suppose we missed some processes, then our simulation will go wrong, right?
Yes.
So before making the like CMS detector, suppose if we are, because such processes we can detect this experimentally, only then we can say. But we are saying before making the detector, these are the process. So how we will go?
Okay. So again, I go back to these things. So we do not know everything. Only I can say that we go this way. These pictures I say, if the Higgs mass is 125, then what do we see? If the Higgs mass is 140, what do we expect? Okay, so before the experiment, we do not know Higgs mass was what. Only we can say the Higgs mass is 125. We will say this signal. Higgs mass is 200 GB. Then I will see the Higgs mass is that. Similarly, this process, many cross sections, we have a predictions, but that prediction might not be correct, as you said. So we have to take this uncertainty that we have that this is the lack of our knowledge. So with that lack of our knowledge, when you go to the experiment, we cannot predict exactly we'll see this scenario because of the lack of the knowledge. This will be little bit fuzzy. I can say that way.
Okay, sir. Okay.
Okay. So now other thing, this is the one simple thing. I say that when this is a colorless particle, colored particle become the colorless, there is a two standard concept. One is this, initially I say that some quark and gluon will come, all of them come together and they combined a form a neutral particles. Other cases, this we call the Harwick generator was used this, and Pythia or the other generator used that individual particle, they will produce this many quark and gluon, and eventually they will combine to produce this neutral hadrons. And also other thing, actually this is the, let's say that initially this quark started with this quark, eventually we'll see this finally, let's say this was interaction occurs, is not, this top is not a good example. Some of this, let's say B quark is produced and B quark eventually go fragmented and gives you this finally neutral hadrons. And what is the neutral hadron? Eventually B quark might be one B quark will be there in this hadron. What is the momentum carried by that B quark? And actually this was this, at present we call this Patterson fragmentation functions. But actually I recall this was the 1978 or 79. Feynman has a big article on this, what fraction of the momentum carried by this meson which is started by this initial quark which is started, that quark will be inside this meson. What is the momentum carried by that? So that this derivation or derived version of this, and also this is the neutral hadrons. Other than that, let for example we say we know that this is the strange particles are produced. How many strange particles are produced? We do not know exactly. Only in the simulation we say that in this experiment, how many k-on and pi-on ratio we see, or k star or rho we see. With that ratio, we can say that what fraction of the strange particle are produced. Similarly, the baryon productions, earlier experiment, how many protons by pion ratio. That's the way we say that when we generate the new simulations, what are these numbers of ratio of this proton baryon versus meson we will see. But as he said that this is this some experiment we see this, we got some prediction, but as the center of mass energy increases, this number is changing. So every experiment when it goes, this is how many strange particle it produce, how many baryon to the meson ratio, that also change. But with this previous experiment, we try to get this prediction, get this number when we start the simulation. Okay, then this is, as I say, that particle are not the, most of the particle are not the stable, and they will decay. It will go to the different decay mode. And this is this, I just say that not complete list. This is the different generators for the different topic, different kind of in physics. There is a many different generators groups. They develop the generators for these simulations. Basically, these two particles, proton or the proton uh, lepton hadron or lepton collider, or let's say a neutrino experiment. All those are, these are the generator. It gives you this, after this initial partons, two parton collide, eventually what are the different particle you will see. So that's, I call that this is the particle level, we call these generators. Then this particle will go our detectors, and there they will go the different kind of interactions. And the different kind of interactions, you people know the photoelectric effect, Compton scattering, pair production. This is the standard. And then this, when the particle goes, it goes the scintillations, absorption, these absorption, reflections. There is many nuclear process it will produce, and the pair productions, and this muon go to the captures, and many more interactions of this hadronic. There is many. This is the picture size of the two hadron interact that produce. Those are the things. So now when these protons of the mesons go to the detectors, these also two mesons again interacting, two hadrons are interaction. So the same thing might happen. So these things, all these process are included in the Giant4 softwares. I'll not go through these at all. So here I'm seeing the Giant4, it has a different processes, and these, even though we say the standard model is well established, but these matter particle interactions, when it comes to the particular hadronic interactions, we are far behind this our true knowledge. And this depends on the many experiment, and some experimental data we use, different experimental data is suitable for the different environment. And this is for this, let's say, electromagnetic interactions. Similarly for the hadronic models, there's a many different hadronic models. As you know, the hadronic is a strong interaction. We do not have the ab initio calculations. This is based on the experimental data and the theoretical model. And here I'm not saying that just go through this, only I'm saying this is the x-axis is 1 MeV to 1 TeV. For the different physics, different energy range for the different particles, people use these different models. Those are included in the Giant4 simulations. So now you have to choose what is your energy range, which particle you want to use. Accordingly, you have to select your physics model. Okay? So I will not go at the detail. This is the standard well-defined techniques was given. So that's the way, only you have to tune these parameters. Okay, and then this is this one of the pictures. I say that when the matter particle interactions, this is the photon comes, it produces the pair production in the material, and the electron projector when it goes, it produces the Bremsstrahlung photon. So like this way it will continue, and then eventually it will produce this what we call the electronic showers. Similarly for the hadron also, this will have the interaction happening, and it will produce the different kind of showers. Particularly only one thing is the hadronic shower is more fluctuations compared to the electromagnetic one, because this is a much more different unknown physics are involved, and this more complicated physics are involved. So these hadronic interactions, our measurement is not very good, but this is the what are the knowledge we have. Based on that knowledge we simulate it. And now when you go to the matter particle interaction simulation, this is the kind of detectors what we are going to simulate. Okay, this is this big detectors. Let's say CMS experiment. When this initially CMS experiment was made, the CMS all these detectors was read out by 77 million electronic channels. I think now it become roughly 120 million electronic channels. And actually this is, I used to tell that in KGF we have this our time scale was microsecond. Now our time scale was nanosecond. Channel number was that time is the kilo. Here is the channel numbers is this mega. And in future, high energy physics electronic channel number will come to the giga channels. That's the way it goes. Okay, so now the detector simulations. Okay, giant, that is I will not go to, even though people know me more on the giant simulation, but I will not talk about at all, because this is a well defined document are there where you can get all this. This is the document where you will get all details. Only thing is that in the giant 4 you have to give the generated events, what are the physics you want to do, and you define your detector material with your shape. And how to define your detector material, how to get your shape. Let for example, this is the simple examples. I have a whole A detector. Inside that A, I am having the 3 detector B, C1, C2. And inside B, I have another detector D. And inside D, I have another detector E. So this is this my T structures. And now how to define a rectangle or the trapezoid shape or the circle. All technique was given in the giant. That's what you do. And then you place one after others. And people used to see call that this is like a Russian doll. Just put one after the others. And that's the way you put it. And giant will automatically take care of all this physics process when your particle go through that. And then you will see this kind of a scenario. Okay, now let's go to the GN simulations. But GN simulation, what it gives, it only gives when these particles go to in your detector medium, how much energy deposited of this incident particle within this medium. It will not give beyond this. It will say that within when it goes here, how much is this energy loss within this medium, that will give. That is not sufficient for us to get our signals. So I go back to the little bit about the CMS. Let's say this is the one quadrant of the CMS in the different view. I just said that this is the 2 new detector. We call this MEG. Forget about what is MEG. This is this double gap gas detectors. This is the gas electron multipliers. There are 3 layers of this gas electron multiplier. 3 steps the amplification occurs. When the charged particle pass through, here it does the ionization energy loss. It produces the some charged particle. When it goes in this medium, within this area, this electron will be multiplied. This is the zoomed of this one of this hole. It's shown here. This here electron will be multiplied. That's the way electron eventually will collect the electron. We collect here anode. We directly collect the signals, direct connection, or we may take the induced signal to get the signal. So this is the three steps are there. Okay. Now we have to start with the proton-proton collision of the vertex and the GN4 simulations. It will tells that when this particle goes here within the deep region, how much energy deposit occurs. I have to start from there, and from there I have to calculate how much signal I will see. And this is one of the, I think I did not put any reference here. Particularly when the high electric field energy deposit occurs, it will produce this electron ion pair, electron will multiply. How much is this average uh, uh, when this particle goes in the medium, how many particles are electrons are produced, and this is the some plots in the standard things we will have. Okay, I just skip this, but the main thing is that this, okay, I will not go in the mathematics because I just keep it as a reference for the students if they want to see in more detail. So the electron are produced, few electron will produce, and when it go to the gas medium in the electric field, in the electric field multiple collision, it will valence. That's we call this, that determined by this Townsend coefficient constant alpha. But also electron, if in this, let's say oxygen or water vapor, electron will attach with this molecule, and then when the electron attached, this negative ion speed velocity will be very, very small because this is the now whole molecule is moving. So we will not have any signal for that. So that we call the loss of signal. So here it defined as the attachment coefficient. So basically, when you say the number of electrons at a distance x with a particular electric field, n become n0 e to the power alpha minus eta x. This is on the average it will go. But now when the real particle will move, there was an here, this is the expression is said there is a 4 scenario kind happen. Let's say a particular distance x plus dx, I have the n number of free electrons. Now it can happen the previous stage I have n minus 1 electrons and only 1 electrons was multiplication occurs, no attachment occurs. Or in the previous stage I have the n electrons, there is no valence, no multiplication, no attachment. Or in this previous stage I have n electrons, but there is one valence occurs, but also one attachment occurs, so the n remain n. It may happen this previous stage I have n plus 1 electron, there is one electron attached, within these steps no amplification occurs. One at that is the no attachment, no amplification, but one attachment. So this is the p n x plus dx is, I can write down, this is this formula, and now from this formula I can write down the differential equations, and that gives you the generalized solution of this. Okay, so this is my expressions. Now when you go to the simulations, really this is, I think, bubble chamber, this is the cloud chamber pictures, how this electron is amplified. You see the signal shape is go like this way, and in this we just try to model is this way, and then these we have to simulate. Okay, and again this simulation, that means all of the random numbers here, my z is my S is a random number. Depending on the random number in the different stage, how many electron we will see, that we have to simulate. Okay, so that's the multiplication, but the multiplication is not all. As I said that when the charged particle goes, it just tell you that how much energy deposit occurs, but how many free electron holes are produced, electron ions are produced, that is GN does not give. That gives by this another package, it called the heat. That gives this how many primary electron produce, and some of the electron may be high energy, it produce the secondary electron, it called the electron hole, electron delta ray, it produce the secondary electron. So this is this how many secondary electron, total number of free electron produced, and what is the distribution of this, that is determined by this heat. Now electron, when we have electric field, this is the simulation of the gem detectors. When the ionization occurs, electron is drifting. Now when it's drifting, it has a constant drift velocity, but it also has a diffusions. So the diffusion also had to taken care of in the simulation, how much it will diffuse. Then this amplification occurs. Amplification I explained earlier, that the way we have to do the amplifications, and these amplifications it was done using the Magballs. And then when it comes to this here, I have this, we see the detector signal we'll see. Okay, but here detector response, when we see this, how much the detector induced signal we will see, or the charge collection will be occurs, that is also is simulated by these Garfield simulators. But most important thing is that if I go back here, these pictures, when the multiplication occurs, in different regions, external electric field is this. But because of this cloud of the charge, positive ion or negative ion, inside this, my electric field configuration is changing. And that's also this continuously my multiplication occurs in the different places, electric field is changing, and this electric field is changed, then my alpha and eta that depends on the electric field, and that's also has to change. So all these has to take care of it. And for that, you need to know what are the electromagnetic field is produced in this amplification. In the different states, that was done by the COMSOL and the NABEAM, and I just have to say the NABEAM, this code was developed by this our SNP colleague, and it was in this, now it is standard CERN softwares. Many people use it. Okay, so these are this all these steps was taken care of in the simulations when in the gem detectors the charged particle has gone through. How much signal we will see in the gem detectors, that we have to do all these simulations. Okay, now I go to the, let's say, the another detectors, a scintillator detectors, where we are more familiar. The scintillator light are produced, and this is this light collected by the wavelength shifting fibers, and the scintillators are put inside in brass chambers, and this is the different layout. Fiber goes here, and somewhere few meters of the clear fibers we collect the signals, and wavelength shifting fibers which is inside the scintillator, the attenuation length is small, but to carry this light it has to splice with this clear fiber. So in the splicing, this may vary, here maybe 90 to 95% signal will transmit it. So all these things we have to take in the simulations. When you do the simulations, now I say like this like this gem, this is the scintillator detectors. The detector has gone. Now you have to see this temperature. We try to fix the temperature. Depending on the temperatures, our light number of photons, how many is produced, that depends on that. And we have an uncertainty of this temperature, so that has to enter in the simulations. Then this electronic noise, intrinsic fluctuations, the few hundred or thousands electrons. Basically, sorry, this is not the electronic noise, intrinsic fluctuation of this number of photons. We say that in scintillators, depending on the scintillator, is 100 to 10,000 photoelectron per MeV produced. That is the average number. Now you have to simulate that on the, in each event, each case, what is this number from that Poisson lambda, you have to produce this n. Now in the scintillator, so when this light goes, in the different part of the scintillators are not uniform. And depending on the position of the showers, the light will be vary. So that's also the depending on the hardware specification, you have to take care of it. Now, what of the fraction of the light when it goes from here to here, there is an attenuations, there is an splicing loss. All these loss factors also you have to take care of using exception rejection method or exponential function to this exponential loss factor you have to take. These are all these light collections. And then when this light is photons fall on this photomultiplier or silicon PM where the light collect, this what is this quantum efficiency? Let's say 30%. Now again with the random number generators, you have to generate that how many photons fall on there, and that gain of this PMT or that's depending on the high voltage. Again, this high voltage we try to control, but what is the uncertainty of the high volt? On that, what are the gain will be variations occurs that you have to take. And here is this actually, I just say the high voltage Hamamatsu with the temperature, how much is this gain is changing. This is this crystals with the temperature, how the light output is varies. And this is the photomultiplier depending on the position, what is the relative output. Depending on different position of the photomultiplier, if the photon falls, output are different. So all this you have to take care of in your simulation to get finally what are the signal you see in your real experiment. Okay, so now here I just said that a few words, my personal, okay, until now, this most of the things it was general, but this is some personal contact. Actually 92, 93, this is the 1992, 93. So that time this as a CMS experiment is not yet approved. And we are studying that when you put the lead tungsten crystals, First of all, this is the lead tungsten crystal. It was chosen using this cobalt 60 and this offshore neutron source. So that gives the confidence that lead tungsten crystal can be used in this CMS experiment. Actually, we are not this only person. There is another group also working, but in India we are involved. Also, what will be the crystal size and how we put these crystals? So here is this some plots. I just, without going in detail, I say that one of the major point is Higgs to gamma gamma. One of the dominant background of gamma coming from the pion. If the pion is two photon coming close by, you cannot distinguish. So then if the crystal size is bigger or smaller, how much we can reject it. So that's why that time we did the simulations. This is one example for the different crystal size. If the crystal size is smaller, then we can have the better pion rejection. Crystal size is bigger, you have the less pion rejections. Of course, we cannot have the very small crystal size because of this Mollier radius effect and also the electronic noise. But this is one of the input we put to design these lead tungsten crystals. And another, from my personal point of view, this is this design of this B-TAB electromagnetic calorimeter. B-TAB was the B physics at Tevatron, like LHC-B. This was the proposals was there, but this eventually this detector did not come up. But this was the detectors. We have this or two arm, and here is the lead tungsten crystals. Many out of these many things contributions. Here is the lead tungsten crystal. First of all, what will be the length of these crystals we should have? This was this length. This was also in this physics. What are the photons will produce? Depending on the photons, if the low energy photons, we do not need the big crystals. If the high energy photons, we need the big crystals, long crystals. Depending on that, in the simulation, we have decided that the crystal length also nearly same as this LHC experiment, CMS experiment. Also, you see this crystal size is smaller than our Cherenkov detector and other detectors. What will be the size of these detectors? And this was optimized to look for this BS oscillation physics. Okay, this is also again a personal task. I am just telling. And this beta proposal time, that time the LHCb did not look this channel as a precisely. And so once in the group meeting, my boss told that this is the one channel what we may look, and then we try to look on the channels. And actually in this proposal, these channels was there, and recently I see this what we decide that time based on the same analysis was done by this LHCb experiment. Okay, that's the different issue. But this gamma is produced, and also this B to Jeff psi eta prime, also BS to Jeff psi eta, eta prime to pi pi eta, all these channels. To have this CP violation in these channels, what is the optimum size we can have? In this experiment, particle is mainly going the forward direction, not many particle going in these sides in this B physics experiment. And so what are the size we will needed for to study for this physics that determines this what is the lateral size of the detectors. But I would say that my most significant contribution on this was in this design, you see the different planes. So these initially, these detectors was put like a planar detectors, but I have shown that if it is the planar detectors, when the shower will develop with an angle, if the shower produced here or shower produced here, my measurement signal will see the crystal here or here. My angle measurement will be completely screwed up. So if I calculate the invariant mass, 4-vector calculation, that will be completely wrong. So based on that assumption, this design was changed from the planar to the spherical shape. So all these things was done without any detector, with our prior knowledge of this instrument, and based on that, this particular electromagnetic calorimeter shape was this is what will be the length, what will be the size, and what is the shape. It was defined based on this. One of the main things, this physics or B2 pi 0, those other physics also. Okay, then. Okay, now I think I overshoot.
Yeah, it's like close to 7:30. If you want to, yeah, maybe you are now talking more of pulse pileup and detector and I mean electronics, noise, etc. Maybe we can just stop at this point, and then
Okay.
or I don't know if you want to finish one slide or but
No, one slide. One slide would not that I'm not finishing.
yeah. No, I was just seeing anyway. It is more of you started talk. Maybe we will anyway cover it in the coming. How much you wanted to cover ideally in this lecture?
In this lecture, initially I said that what was there. So the two lectures, the simulation, I put one of these.
Okay.
But I think I know it will not be
Construction in the second one, right?
Yeah. So that was the initial thought.
Okay.
But I may not be. Okay.
No. Maybe what I meant is, I don't think you should go fast, and then it will not serve the purpose. But
then I think I'll stop here. I think this is
maybe we have to have 3 instead of 2. But let us plan. Maybe because let us take a few questions if there are any from Zoom or YouTube. There's one question. I don't know if you want to take that up.
Yes.
How to determine the neutrino flux spectrum with GN4?
No, GN4 does not take care of the neutrino flux spectrum at all. The GN4 cases, the neutrino does not, according to the GN4 simulation code, neutrino does not interact with the matter.
Okay. So that's not something you can infer from.
Yes.
Okay. Any questions from the especially students on the Zoom?
Yeah, sir. Can I ask?
Yeah. Please go ahead.
Yeah, sir. In the beginning, when you are explaining this T random 1, 2, 3. So in T random 3, there are many. For example, in T random 1 and 2, we are having 2 or 3 variables.
Yes.
So can you explain again what is this T random 3? How this?
We just skipped.
Yeah,
okay. So this one is okay. As I say that here, I would say that MZ is this is a 2 initial random number C do use.
Yes.
Of this here it is 3 or 4, and here this initial random seed is 263. Okay. Okay. The only simply I can say the initial is 263 seeds will be there, and that's the way it will go. Okay. I did not put this paper reference. I will put in the paper reference. And okay, truly speaking, if you ask, I do not have any answer more than that. Other than I say that this will go nearly the same technique is this, but it started with 263 numbers.
Sir, in T random 2, you are saying that they extended 3 and 4 variables.
Yes.
So is it sometimes 3 and 4 or it randomly, like what is this?
So this is the MZ and MW. This is the 2 seeds.
Yes.
So let, for example, is a seedless or a MLCG. I started with 1 seed.
Yes.
But here I started with the 2 seed. MW1, MW2, so 2 numbers, arbitrary number. It returns me my sequence of random number.
Yes, sir.
So here this will be the 3 or 4, and here it was the 263.
Suddenly quite a large.
Suddenly a large jump.
My question is 3 and 4. You are saying, I think we should fix like it should be some like fixed some extended 3. Either we should take 3 or 4.
Okay, these are both options are there. That's what I'm saying. In this package, it says that you go either 3. This is the one random number generators, and 4. It can go 4. Oh, you are saying the T random 2. What they use?
Yeah.
I think they use 4. Okay, I'm just the 3 and 4. This is I talk about the paper, what they talked.
Okay.
Kulahal, do you have any questions?
Hello, sir. Actually, yes. So I was not sure if I'm audible here.
Can you lower your volume or go little away from the mic?
Okay, so can you hear now?
No, but very, very noisy. Is it possible to type in your question quickly?
Yes, I'll just type it.
Okay, Kolal?
Yeah, he's just typing in
Okay.
quickly.
Okay. If there by that time, if there any other question, you
Yeah, that's what. So any other questions? I'm going to. Okay, no, not yet come. Yeah, something I think came up.
Yeah.
Is there any plan on GR4 community to implement magnetic field coil, which will self-generate field inside the detector?
To my knowledge, it is not there. Okay, I am okay. This is the I said to my knowledge. I do not think that they are planning anything on that.
Okay, sir. Actually, I just wanted to know that because sometimes it is helpful if the field is already there, or I can design all myself. So that is why I was asking. Okay, thanks.
Okay. Okay, then Gobinda, then maybe
Okay.
we'll kind of close today's lecture at this point of time. And so again, let me remind all of you that the next talk is going to be very next week, that is on Monday. He is going to, I mean, hopefully he's going to continue from here, but then let Mr. Gobinda decide how he is going to kind of try to cover the simulation.
So now, as I told you morning, I think now it looks like it will go 3. Okay.
That's fine, because the reconstruction is also something which
No, particularly not only reconstruction. I just want to tell student about the how do we calibrate the instrument in the runtime or the before that.
Okay.
So this is the okay. This is this without any calibrations we cannot validate that what we get the experimental data. Experimental data.
Yes.
That calibration is then one of the important topic. Okay.
Okay.
So next day I will start from here where I stop, particularly this digitization and our INO that Gini simulations.
Okay.
Okay.
So thank you, Professor Gobinda, and also thank you all of you for joining. So let us join again next Monday for continuation of. I mean, today we had to stop, so continuation of the simulation.